Yeah, okay, so let's start. Share my screen. Is my screen visible?
Not yes.
Okay, yeah. So yeah, as usual, we'll first recall what we saw in this week and what we'll need for this session. So this week we saw communication complexity, and in particular we saw the two-party communication model. So for the two-party communication model, we defined a protocol pi as follows. So I'll just give you an informal idea of what a protocol is. I won't define it formally. So we saw that to compute a function f from 0, comma 1 to the n to 0, comma 1 to the n to 0, comma 1, two parties, Alice and Bob, having inputs x and y, send messages to each other. I'll number these messages A1, A, B2, A3, B4, and so on. Now, each message sent by Alice, that is AI, only depends on x and all the previous messages. Similarly, each message sent by Bob, this should be y. Each message bj sent by Bob depends only on y and all the previous messages. Finally, we said that a protocol computes f if the value of the function f of x comma y is clear from the transcript of the communication. So after that, we saw what the deterministic communication complexity of a function f is. So it's denoted by df, and it is minimum over all protocols pi, maximum over all xy of the number of bits used by pi to compute f of x comma y. And we also saw the notion of a protocol tree. So a protocol tree is a way of pictorially describing the execution of a protocol. And the important things that we need to know about a protocol tree are that each root to leaf path in the tree corresponds to a unique transcript of pi, and each leaf corresponds to an output of the protocol. So it's a binary tree with it's a directed binary tree with its edges that directed away from the root. So a root to leaf path makes sense. Then we saw some methods of proving communication complexity lower bounds. The three methods that we saw were the Fulling set method, the tiling or monochromatic rectangle method, and the rank method. We also saw some applications of communication complexity, but I won't recall these because we don't have any questions related to those applications. So if this is fine, we can move on to the problems.
Yeah.
Yeah. So the first problem is in the two-party communication complexity model, what is the computational power of the individual parties Alice and Bob? The options are both are log space Turing machines, both are both are, both are polynomial time Turing machines. Option C, both are polyspace Turing machines. Option D, both are exponential time Turing machines, and both have unlimited computational power. So this is just a recall question. What's the answer to this question?
E.
Yeah, both have unlimited computational power. So in computation complexity, we're not worried about how Alice and Bob go about computing things. The only thing that they worry about is how much you have to communicate with each other to compute things. So yeah, the answer is B. The
So
second
I have
problem,
a question over here.
right?
So if we take the computational landscape, either things are
Hmm,
computable or non-computable.
right,
So, and in the computable landscape, everything falls in one of the class.
right.
So, so in this context, what is the meaning of unlimited computational power?
Okay, so by unlimited computational power, you mean that they can basically compute any recursively enumerable function. So, for example, using okay, so the communication complexity of the halting problem is just constant. So, because
Yeah,
let's say Alice has infinite computational power, so it can uh, decide the halt language. Sorry, it can accept halt language, right?
yeah,
Yeah, so we are not worried about the computational power of individual parties. Yeah. So the second problem is suppose Alice and Bob need to need to compute a function f from 0 comma 1 to the n cross 0 comma 1 to the n to 0 comma 1. They use the protocol pi to compute f. Which of the following choices indicates the worst case number of bits communicated by pi? The number of ones in the matrix MF, the number of nodes in the protocol tree, the height of the protocol tree, and the number of leaves of the protocol tree. So what's the answer to this problem?
Height of the protocol tree.
Yeah, right, that's correct. So you would have seen this in class, but let's quickly go over the argument. So the argument is the following. Every root to leaf path in the protocol tree of pi corresponds to the transcript of
Script has to
pi's execution on some input, comma y in 0, comma 1 to the n cross 0, comma 1 to the n. The length of the path is equal to the number of bits communicated by pi compute rather compute f of x comma y using pi. Right. So we are interested in this quantity, right? Max over x comma y. I am not writing the domain just for the sake of brevity. Max x comma y number of bits communicated to compute f of x comma y. So because of this, this is just equal to max over all paths, uh, max over length of max over all path p, length of p, right? Here p is a root to leaf path, right? And this is just equal to the height of the tree, right?
Yes.
Right. So the answer is the height of the tree. So the next problem is the following. So from problems three to so from now on, the problems would require some proof or some working out. So these would be slightly lengthier. So let f and f prime be two functions from 0, comma 1 to the n cross 0, comma 1 to the n to 0, comma 1. Suppose f prime xy is equal to fxy for all values of x and y in 0, comma 1 to the n, except the case when x and y are both the zero string. That is, both are the all zero input. Which of the following statements is or are true, select all that apply. The communication complexity of F is equal to the communication complexity of F prime. The communication complexity of F is uh, less than equals to the communication complexity of F prime plus 1. The communication complexity of F prime is less than or equals to the communication complexity of F plus 1. The communication complexity of F is less than or equals to the communication complexity of F prime plus 2. The communication complexity of F prime is less than or equals to the communication complexity of F plus 2, or none of the above can be inferred from the information provided. Now, as I said, this needs to be worked out, but would you like to venture a guess on which option or which options are correct?
Uh, I cannot see straight away.
Yeah. Okay. So let's. Okay. First of all, okay. Let me ask you the simpler question. Suppose this holds. Okay. Suppose B is true. Then should C also be true? Okay. There is no difference between F and F prime, right? This situation is symmetric,
Yeah.
right? I could as well replace F prime by
Yes.
F. Nothing would change,
Yes. Yes. Yes.
right? So either this is true, or this is true, or both of these are true, or both of these are true, right?
Yeah.
Yeah, so now let's see which are true. The answer is D and E, and let's see why. So, yeah, let pi be a protocol to compute F. Consider the following protocol pi prime. Uh, if Alice is input, yeah, let X be Alice's input and Y be Bob's input. If X is equal to 0 to the n, the, the first bit that Alice sends to Bob, or the first message that Alice sends to Bob, is 0. Otherwise, it is 1. Okay, similarly, y is 0 to the n, then the first message that Bob sends to Alice is 0. Otherwise, it is 1. Okay, so far one round of communication has happened. Alice has sent a message, Bob has sent a message. Now, if uh, both messages were 0, the protocol terminates. Otherwise, Alice and Bob execute uh, pi on input, inputs X and Y. So is the protocol pipeline clear?
Actually, I'm confused that there are two functions f and f prime.
Right.
So what I'm confused about is that what is the function that is being computed by Alice and
Okay,
Bob jointly?
right. Yeah. So let's consider the following protocol F prime or F prime. So what I'm doing is I have a protocol for okay. So I want to find some relations between the complexity of F prime and F, right? So what I'm doing
Yes.
is I'm starting off with a protocol for pi, protocol pi for F, and designing a protocol pi prime for F prime. Okay,
Yeah.
right. And right now in this situation that I just mentioned, they're computing F prime using the protocol to
Yeah.
compute F. Okay,
Yeah.
right. So is the protocol pi prime clear?
Yes.
Right. Now
So pi
let's
prime is computing F prime
right
using F. I
using
mean
pi.
pi. Yeah.
Right. Okay. So now so if the protocol is clear, we need to show two things. Right. Number one, pi prime actually computes F prime. That is, it correctly computes F prime, right? And number two, that it has its communication complexity, so the number of bits it sends is at most 2 plus the number of bits that pi sends, right?
Yes.
So let's do the first thing. Claim 1, uh, pi prime correctly computes F prime. True. So there are two cases. Uh, case 1, the first two messages are both 0. Okay, what does this mean? This means that x comma y is equal to 0 to the n comma 0 to the n. So after these two bits have been communicated, Alice and Bob know that the input is 0 comma what 0 to the n comma 0 to the n, right?
Yeah.
Right. So uh, further, after the messages have been communicated, f of the value of is clear, right?
Yes.
Sorry, f prime x comma y because they're computing f prime. It is f prime 0 to the n comma 0 to the n, right?
Yeah.
Yeah. So in the first case, what does our protocol do? It just communicates these two bits and stops. But because the moment these two bits have been communicated, the value of f prime is clear. The protocol computes f prime in this situation correctly, right?
Yeah.
Yes. Case two. At least one of the first two messages was 1. In this case, this means that f prime, okay, let me write it, but just put x and y. This, what does this mean? This means that x comma y is not equals to 0 comma 0, right?
Yes.
Right. And what do we know? So f of f prime x comma y is the same as f of x comma y, right?
Yes.
Computes pi, computes f using pi, not pi using f. Computes f using pi. It correctly computes f prime x comma y in this case as well, right? Is this okay?
Yeah.
Yeah. So we have proved the claim that pi prime correctly computes f prime. Okay.
Yes.
Now we are interested in the like the combination complexity of pi prime, right?
Yeah.
Okay. So now we'll prove this is less than equals to plus 2. Okay. Let pi be the most efficient protocol computing f. Okay, so pi is the most efficient protocol to compute f, or pi is one of the most efficient protocols to compute f. There can be multiple protocols. What does this mean? This means that the number of bits that pi sends that is equal to df, right?
Yes.
The complexity of pi is df, right?
Yeah.
So let pi prime be constructed using prime. Okay, so I'm using pi to construct pi prime, right? The most efficient protocol to construct pi prime. Claim one implies,
Yeah. So, so one thing is more clear over here that the
right?
computational complexity of f prime should be at least the computational complexity of f.
Yes, right.
Yeah.
That pi prime be constructed using pi prime. Claim one implies that pi prime correctly computes pi, right?
Yeah.
Okay, so now what we'll do is we'll find out how many. Okay, so let me write it like this. So t of f prime is upper bounded by this quantity, right? Max over x comma y. I'm again not writing the domain of number of bits communicated by pi prime to compute f prime x comma y. Why? Because the communication complexity is minimum over all protocols. Here are one protocol, so it's obviously upper bounded by this quantity, right? Well, better protocols can exist, but this is at least one protocol. So this is an upper bound. Are you? Is this fine?
Yeah, yeah.
Yeah. So now we just need to find out the number of bits communicated by pi prime. Okay. So we'll count uh, the number of bits communicated in two cases again. Case one. Hmm. The first two messages. Okay. There is a better way of writing these cases. X comma y is equal to 0 to the n comma 0 to the n. In this case, pi prime just uh, communicates two bits, right?
Yes.
So, and in case two, uh, in this case, two plus the number of bits. Is this fine? Because what does the pi prime do in this case? It first would have sent a message that the first two messages would have looked like 0, 1 or 1, 0 or 1, 1. And after that, uh, pi, pi prime just executes pi, right?
Yeah.
So the first two bits are accounted for over here and the rest over here, right?
Yes.
So in both of these cases, this is upper less than or equals to d of f plus 2, right?
Yeah.
Over here it's d of s plus 2 because d of s has to be at least 0, right? It
Yes.
can't be a negative number. And here it's clear why it's d of f plus 2. Right. So what does this tell us?
Yeah.
So d of f prime, let me clear. And I was mentioning before, we can repeat the same argument by switching f and f prime, right? This would be
Yeah.
d of f is less than equals to d of f prime plus 2, right? So yeah, these were the two answers, right?
Yeah.
Yeah. So let's move on to the next problem.
So here,
Yeah.
just can we say that in general, two Boolean functions which are just not equal at one point their
Hmm.
communication complexity is separated by a constant.
Yes. Because instead of 0, comma 0, let's say they were separated into x, comma y, right?
Yeah,
Or let me call that x star, comma y star to distinguish with normal strings. And what you could have done is, if LS's input is x star, it sends 0. If, otherwise, it sends 1. If Bob's input is y star, it sends 0, otherwise, it sends 1. And then it's the same thing, right? If both are 0, stop. If at least one message is 1, execute the protocol pi, right?
yeah.
Yeah. So I think there is nothing special about 0 over here. So consider the function f 0 comma 1 to the n to 0 comma cross 0 comma 1 to the n to 0 comma 1. That is the following property. For any x comma y in 0 comma 1 to the n, we have that f of x comma y is g of x, where g is a function on a single input. So g is from 0 comma 1 to the n to 0 comma 1. In other words, the value of f is independent of the value of y. It just depends on the value of x, L is his input. Further, suppose that there exists x prime and x double prime in 0 comma 1 to the n, such that gx prime is equal to 0 and gx double prime equals 1. There should be a full stop over here. What is the communication complexity df of f? The options are 0, 1, 2, n over 2, n and n plus 1. So again, this needs to be argued, but would you like to take a guess what the communication complexity is? Oh, I showed you the answer.
Uh, I think some constant because f for f we don't need to communicate. F
Right,
is depends only on x, so Alice
right.
can compute it locally actually,
Yes. And then, so let's say Alice computes it. What would it do? What would she do then?
and then she can communicate its value to Bob.
Right. So how many bits are communicated?
Uh, if the size of f 0 0 1, so just one bit.
Right, exactly. So the answer is 1. And the reason is exactly what you said. So Alice has X. So she can compute GX and send it to mom. Uh, as y is in 0, as y for all y in 0, 1 to the n, f of x, y equals gx. The function value is clear from the transcript of the communication, right? Just this communication, sending this g of x to
Yeah,
Bob, right? Hence, d of f is at most 1, right? But we still need to show that it's not 0, right?
yeah,
And that's why recall that there were two x, one x prime and x double prime, which had different function values, right? That's where this those come in handy. Now, because
yeah,
there exists x prime and x double prime, such that g of x prime is 0 and g of x double prime is 1, the communication complexity of f must be greater than 0. For if S. Alice doesn't send any bit to Bob, he has no way of finding out whether Alice's input is x prime or x double prime, right? So Alice
yeah,
has to send at least one bit to Bob, right?
yes,
So that implies that d of f is at least 1, and combining it with this, you get d of f is exactly 1. Yeah.
yeah.
So let's look at the next problem. Consider the function f from 0, 1 to the n cross 0, 1 to the n to 0, 1 defined as follows. The function is equal to 1 if and only if x plus y read as an n plus 1 bit binary number is a multiple of 8. What is d of f? It's an n plus 1 bit number because when you add two n bit numbers, you might get an n plus 1 bit number. Yeah. So the options are 2, 3, 4, 8, n over 8, and n plus 1. Again, this needs to be worked out, but would you like to take a guess? Or if you can't figure out what the exact values, at least say something like order log n or something like that.
Um, One thing is that if the number is divisible by 8, then last three bits should be
Exactly.
0 0 0,
Right.
and So
Yeah,
maybe 3 bits we need to communicate.
yeah, you are very close. The answer is 4. Oh, so the answer is 4. And let's see why. Why we need this one extra bit. Okay. So, as you said, x plus y is divisible by 4. Sorry, divisible by 8. Divisible by 8 if and only if the last 3 bits of x plus y are all 0. Now, if, okay, let me like this. Okay, what do the last 3 bits of x plus y depend on? So the last 3 bits of x plus y just depend on the last 3 bits x2, x1, and x0 of x and y2, y1, y0 of y, right? So now consider
Yes.
this Alice sends x2, x1, and x0 to Bob. Bob computes this number x2, x1, x0. So when I write x2, x1, x0, I don't mean the product, but I mean the number x2, x0, x1. Okay, plus
Yeah.
y2, y1, y0. If this sum is 0, then, okay, what should Bob do? 0, otherwise he sends 1. Okay, this is a protocol. Is the protocol clear?
Yeah.
Yeah. Now observe that after the protocol is executed, the value of Alice and Bob, right?
Yeah.
Yeah, because if Bob sends 0, then they know that the number is divisible by 8. And if Bob sends 1, then they know that the number is not divisible by 8, right?
So this convention is prior to setting up the protocol. This convention is agreed upon by Alice and Bob.
Okay. So the protocol is agreed upon beforehand, right?
Yeah.
So pi is the protocol. Even before Alice and Bob get their input, they agree upon what pi is. Okay.
Yeah.
Once they get input, they would instantiate pi. For example, the way I've defined pi over here, I have things like x2, x1, x0, and so on, right?
Yeah.
So Alice and Bob have this string with them. Then they get their inputs. So then x2, x1, and x0 have concrete values. Y2, y1, and y0 have concrete values, right?
Yeah.
Yeah, so that becomes an execution of the protocol, right? So the protocol is agreed upon, but the execution can only happen after they get their inputs.
Yes, yes.
Yeah. So observe that after the protocol is executed, the value of f of x comma y is clear to both Alice and Bob. So this means that d of f is upper bounded by, sorry, 4. 4 because if Bob doesn't send anything back to Alice, then Alice won't know the answer, right?
Yes.
Yeah. And okay, so that tells us it's at least 4. What about 2 and 3? So while this can be formally argued as well, why it's 4, I'll just give you a rough argument, okay? So T of f is greater than equals to 4 because Alice needs to send 3 bits of information, right? Because if Alice doesn't send any of these 3 bits, or if Alice does anything else, then Bob can't be sure that the 3 bits, there's these 3 bits are zero. These 3 bits and these 3 bits add up to 0, right?
Yeah.
Yeah. And so this tells us that at least 3 bits are required. Also, if Bob doesn't communicate, function value, right? So at least 4 bits need to be communicated. Is this fine?
Yeah.
Yeah, I mean, this is not a formal argument, but this can be made formal. Yeah, so let's move on to the next problem. So the next problem is the following. Consider the average function avg n x comma y, where x and y are in 0, 1 to the n. The function average x comma y is the arithmetic mean of the multiset x union y. So what is the set x and y over here? For example, if n is equal to 4 and x is the string 1011 and y is the string 1100, this means that the set x is 134. So what we'll do is we'll treat this string as a characteristic vector for this set 1, 2, 3, 4. So the set is 1, 2, 3, 4. Because the first bit is 1, 1 is in the set. Second bit is 0, 2 is not in the set. Third bit is 1, 3 is in the set. Fourth bit is 1, 4 is in the set. And similarly, y is 1, 2, 4. Now, what is the multiset x union y? It's 1, 1, 2, 3, 4, 4. And the average is just the sum of all of these divided by the size of this set. So that's 2.5. Okay, so is the average function clear?
Yeah.
Yeah. What we are supposed to do is show that the communication complexity of average is order log n. So there is a protocol that can compute average in order using just order log n many bits of communication. So is the question clear?
Yeah.
Yeah. So let's show this. So yeah. So observe the set x j such that the jth bit of y is 1, right? Is this clear?
Yeah.
Yeah. Hence, so this is just this expression, sum over, no, let me do some other index. Yeah, I think this p in x, right, plus sum over j in y, j over size of x plus size of y. Is this clear? Why? Because this is the sum of all elements in x. This is the sum of all elements in y. So this is the sum. And this is the size of the multiset, right? So we are dividing the sum by the size of the multiset. That's exactly the average.
Yeah.
Yeah. Okay. So here's the total. Take and then compute. Right? Is this fine?
Yeah.
Yeah. Okay. So now let's look at how many bits are communicated using this protocol, right? So this correctly computes average. Now we need to find out the number of bits communicated by this protocol. So yeah. Okay. So x and y are both subsets of n. This means that size of x and size of y is less than equals to n, right?
Yeah.
So these two sizes are order log n bit numbers, right?
Yeah.
Okay, fine. Now, uh, this sum is upper bounded by n square, right? Because, like, in the worst case, the size of x is n, in which case x is just 1 to n. If you sum up 1 to n, you get n times n plus 1 over 2, which is less than n square, right?
Yeah.
So this is less than n square, and this is also less than n square by the same argument. Okay,
Yeah.
so
So
the two
we'll need
sums,
log n square bits.
right? Order log n square bit numbers. Order log n square is just 2 times order log n, right? So this is also log n bit numbers.
Yes. Yes.
So the number of bits communicated, this is like 4 times order log n, because there are 4 numbers, right? Size of x, size of y, the two sums. which is just order log. Okay,
Yeah.
yeah. Now let's move on to the next problem. So the function disjointness denoted by dijn of x, y, where x and y are in 0, comma 1 to the n is equal to 1 when the sets corresponding to x and y are disjoint and 0 otherwise. So the sets that correspond to x and y are just the capital X and capital Y that we saw in the previous question. In other words, the function disjointness of x comma y is 0 if and only if there is an index I, there is an index I in 1 to n such that xi is equal to yi is equal to 1 and 1 otherwise. Okay. Show that the deterministic communication complexity of this function is at least n using the Fooling set method. Okay. Is the question clear?
Yeah.
Yeah. Okay, so let's prove this quickly. Mm, okay, so claim one. Okay, so for the Fooling set method, we are just supposed to design a Fooling set and compute its size, right? So let's design the
Yes.
Fooling set. A is this. So by x bar, I mean x complement, the complement string of x. Okay, so let's quickly recall the definition of Fooling set. 0, comma 1 to the n. Uh, S subset of again 0, comma 1 to the n. Set to be a Fooling set if and only if for all x comma y in uh, S, f of x comma y is same for that uh, and for all x comma y, x prime comma y prime in S such that x comma y is not equals to x prime comma y prime. Uh, no, 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 at least is not equal to. So this is the definition of Fooling set, right?
Yeah.
Yeah, so now we want to prove that A is a Fooling set for this function. Okay, so for all x in 0, comma 1 to the comma, what is this value f of x comma x prime? Sorry, f comma x bar.
It should be 0.
Yeah, this is 0 because the sets corresponding to x and x complements are complements of each other, right?
Yeah.
So the first property is satisfied, right?
Yeah.
Yes. Okay, so now let's do the second property, okay? Okay, so what should this value be?
Um,
Yeah, 5? Yeah, it's right, it's 1, but why? Okay, so the reason is the following. I mean, you can also do it using sets, but I find it easier to do it using strings. Now the okay, if okay, because uh, x I not equals to xi prime complement for all I in n, this implies that okay, so when is it possible that two strings disagree at every point, at every bit? It's only possible if they are complements of each other, right? So this is only possible if x is equal to xi prime complement, right? Which is the same as saying x is equal to x prime, right? So is this argument clear? Hello? Yeah. So this is a contradiction, which so what does this tell us? This tells us that A is the Fooling set because it satisfies both the properties. Now, oh, I'm out of space. Yeah, so this tells us that both properties are satisfied. And now recall that d of f is greater than equals to no. So in this case, the deterministic communication complexity of disjoint n is greater than equals to order size of A, or sorry, order long size of A, and size of A is 2 to the n because for every x in 0, 1 to the n, it contains x bar. So this is order log of 2 to the n, which is order n. And that is exactly what we wanted to show, right? So yeah, we are out of time. So let's stop for today. If you don't have any questions, we can wait till next time.